that lead in treatment very well. Okay, so almost always the treated water going out into the system is very clean with respect to lead, and that's usually not an issue. Okay, so in a perfect world, this nice clean treated water would go through our pipes, arrive at our faucets for us to enjoy. Okay, but of course there are instances where we do have lead contamination, all right, where the solid metal lead in the pipes, represented by the chemical symbol Pb, okay, leaches out into the water in its ionic form, Pb2+. Okay, this is water soluble, and that's what leads to the contamination, and that's what we receive through our faucets. Okay, so the question is, what can we do about this problem, and how can we prevent it in the first place? Okay, so as Dr. Tritico alluded to replace all of our lead-contaminated pipes would be extremely expensive and impractical. Okay, so thankfully, there's a much simpler and cost-effective solution, at least in the short term, okay, which is to simply coat the interior surface of the pipe with a corrosion-resistant material that would prevent the water from even coming into contact with the metal pipe. Okay, so how can we generate this protective film? Okay, well, tap water contains naturally calcium, which we associate with water hardness, right, and carbonate ion, which we associate with alkalinity. Okay, these chemicals are naturally present in the treated tap water, and they're perfectly healthy. In fact, we have a lot of these chemicals, high concentrations in our own blood. Okay, so nothing problematic here. Okay, and when calcium comes into contact with carbonate, they form a marriage to make calcium carbonate, which is basically chalk. Okay, so by this reaction, we're forming a white chalky material that can coat the interior surface of the pipe. Okay, and this acts as a protective barrier, so again, the water can't even come into contact with the actual metal surface. Okay, so this is a really desirable situation. Okay, and so we want to have just the right levels of hardness and alkalinity to generate enough calcium carbonate to coat the pipe, okay, but not so much where we're actually clogging it up with too much material. Okay. All right, and so what happens when we have lead contamination, okay, the typical problem is usually mainly alkalinity. All right, usually there's plenty of calcium to generate the calcium carbonate, but when we have corrosive waters, okay, that can leach the lead, what that corrosive water means is that it's usually acidic, okay, which correlates with low alkalinity. Okay, so there's not enough carbonate to generate this protective film. Okay, and if the water is corrosive enough, it can dissolve any film that is present and start to leach out the lead. Okay, and so thankfully there are solutions when our alkalinity is running low. And there's different chemical agents that we can add. For example, caustic soda, also called sodium hydroxide, or phosphate, or other chemicals that can reduce the acidity, okay, and help bring up the level of the alkalinity, so we do have enough carbonate to generate this protective barrier. Okay, so chemically, it's really not terribly difficult, but of course it is a much bigger challenge in a large-scale drinking water and distribution system. So to get the balance of all these things right is a little bit challenging on that large scale. Okay. Right. It is a little bit ironic because in the pipes we do want to generate this calcium carbonate, but on our houses we do not, okay, because calcium carbonate, this filmy material, is the same thing that generates soap scum in our showers and streakiness on our silverware when it comes out of the dishwasher. Okay, so we want to avoid that in that context. And so to eliminate some of that hardness that produces it, most of us have a water softener maybe down in our basement to prevent that from happening. Okay, so there is a little bit of balance, but I think we all agree that we would trade a little soap scum on the shower to have lead-free water, right? Okay. One other thing I'd like to touch on as we wrap up is to just consider, when we talk about lead contamination, how much lead are we actually talking about in the water? Okay, so the EPA limit is a concentration of 15 parts per billion, okay, as the concentration of lead. So one way we could think about that in a theoretical sense is that if we had water that was 15 parts per billion, if we had 1 billion pounds of water, it would contain 15 pounds of lead. Okay? Or maybe a more practical way of looking at this, if you wanted to drink enough 15 ppb lead water, okay, to generate enough mass of lead the size of a dime, you'd have to drink over 250,000 20-ounce bottles of water to get enough lead just to give you the lead the size of a dime. Okay? So when we're talking about part per billion concentrations, we're talking about extremely low concentrations, even in contaminated situations. Okay? But of course, a lot of chemicals like lead can have health consequences even at some of those very low concentrations. So it is something to be concerned about. But the really low concentrations are the reason why, when there's questions about lead contamination, we often have to send the samples off to a lab somewhere to be tested, because the instrumentation that required to analyze for lead is extremely expensive and sophisticated. And so we can't just do it on site. In some of our local municipalities, it has to go off somewhere for this more rigorous testing. So with that, I'll be glad to address questions with the rest of the group at the end, but for now I'd like to turn it over to Dr. Kumar for our next segment.